Thank you, Professor Carlos, for the introduction. So the talk, I'll try to be very brief with my talk because we have to be on time. But so let's just start with something. So we know that black holes are very weird objects, right? So that's why we study. And of course, it has a lot of implications for a lot of other things in physics, like thermodynamics, particle physics, string theory, and mostly fundamental physics, right? And of course, nowadays, with gravitational waves, we actually have some astrophysical interest as well, because we know that we can detect gravitational waves from in spirals from binaries of black holes, right? And with that, we can probably maybe get some deeper understanding of nature by studying black holes and gravitational waves. And if we combine those together, we know that you have a scenario usually of very high energy, and we can potentially test some new physics. And well, at least I like quantum field theory as well. So we can use quantum field theory in curved spacetimes to learn a lot about these objects. And we already know that this can help a lot. So for instance, we know nowadays that black holes radiate, and that the particle, which the Hawking radiation, right? And also that the particle content of a theory is actually an observer-dependent concept, which is the Unruh effect, right? And I won't extend too much on that, but please see João Paulo's talk about that. I think he will talk a little more about that. But why study Schwarzschild de Sitter spacetime, right? The thing is, we know that the Sitter spacetime is an interesting model to study the early universe, because we know, at least it seems that our universe in the beginning was exponentially expanding. And also, if we think about it, our universe will probably become a lot more like the Sitter spacetime in the late times of its evolution, right? Because it's accelerating, it has an accelerated expansion. And sorry. Yeah, so we know that black holes and their dynamics in the early universe are still more or less poorly understood, and we can try to combine those things and study some stuff about them. So for instance, we can use a simple model with a scalar field. So we will try to study a scalar field around Schwarzschild de Sitter spacetime, which of course it's a spacetime with a black hole in it, and you have a positive cosmological constant, which basically which is related to the Sitter spacetime. And the thing is, if you try to extend massless fields to curved spacetimes, usually what you want is conformal invariance, right? And the problem with that is if you consider minimal coupling, you don't get conformal invariant unless your spacetime has a Ricci scalar, vanishing Ricci scalar, right? Which is not the case in the Sitter spacetime. So you have non-vanishing Ricci scalar, so you have to address non-minimal coupling in that case, which is what we are going to do right now. So I don't know if the video is going to work because our yeah. So maybe I should. Right. So this is just a LIGO animation, right, that I took from their website, which basically explains what I'm been talking about right now. So you have two black holes, and they they collide with each other and you produce gravitational waves. And so what exactly are gravitational waves, or at least how we are going to study? So you consider the fabric of space-time, right? And what you consider to be gravitational waves are those undulations on the fabric of space-time itself. And those waves actually propagate at the speed of light. Usually you can consider them to be very small, and you can write it like that. So you have the space-time metric, which is, you are going to consider it as a background space-time metric plus a perturbation, and you have an equation of motion like that. So it's basically a wave equation in a curved space-time. So what we are going to do is consider the background space-time metric as Schwarzschild de Sitter space-time, and study perturbations on that, right? So this is just an illustration. So the first guy to actually try to detect gravitational waves was this scientist, so Joseph Weber, and he tried to do that with a more or less simple experiment, right? So you have a very large aluminum bar and you have some transducers, and what he was expecting to detect was you get a gravitational wave, and you can measure the relative motion of the parts of this aluminum bar using those transducers, right? And of course it can work like that, but actually the effect is much too small to be detected. But he published some papers about that, stating that he detected gravitational waves. And one problem with those detections is that if you consider gravitational waves in if you consider gravitational waves using those Weber observations, the problem is that the energy emitted would be very, very high, and because the gravitational waves actually emitted in quadrupolar form, right? And so for those for this emitted power to get to Earth with that value that Weber detected, it means that almost all the universe energy would be emitted in that event. So of course this doesn't make sense, right? And one way to explain those values is actually, instead of a small portion of energy getting to Earth, you actually have a very high concentrated portion of energy from that event getting to Earth, and you are actually measuring that. And one way of doing that is by synchrotron radiation, right? So what is synchrotron radiation? So the usual way we study synchrotron radiation, you have an electron and you accelerate it in some fashion, usually some circular or elliptic motion, and via its acceleration is actually emitting electromagnetic radiation in a very concentrated angle of emission, and you can try to do that with a gravitational system, right? And so if Earth is actually in the plane of emission, you can get something as that could explain the value of Weber observations, right? So the value of emitted power that was getting to Earth. So usually you do that in very large laboratories, and usually they have the size of a football field, right? So this one is our national lab for that, it's Sirius. So, and you can collect the radiation from the electrons that are being accelerated in the laboratory. And yeah, so that's the mechanism that was proposed by Misner. So you have particles orbiting in a black hole. They reach very high velocities, and you can emit large amounts of gravitational waves, and they are concentrated in a narrow angle. And these radiations is what is actually getting to Earth, and you can explain the emitted power from the observations, right? So this is just an animation. That's basically what is our setting, right? So you have a particle, and it is orbiting a black hole in the space-time, and it's actually emitting some quanta of a field, right? And so this is the de Sitter space-time, Schwarzschild de Sitter space-time. It's very similar to the Schwarzschild space-time, but the radial function is actually a little bit different because you have this third term in the f of r function is dependent on the cosmological constant. Yeah, and what is very different from these solutions is that you actually have two horizons, right? You have the event horizon of the black hole and the cosmological horizon, which is basically the limit of your observable universe in this case. And you have an existent region for time-like circular geodesics. So because we are trying to study those circular orbits, you have to consider those values, right? So as you increase the cosmological constant value, which is this lambda, you actually narrow the portion of your space-time in which you can have time-like circular geodesics. So I showed to you the perturbation of the gravitational field, right? So, but what we are going to do here is study a simpler thing, which is just a scalar field, a massless scalar field. But of course, you expect some behavior from that to extend to the gravitational case. So this is just the action, right? So some technical details I'll just go very quick. So you have the equation of motion is just the Klein-Gordon equation with a coupling to the Ricci scalar, and to study that you can use separation of variables, and we are going to do that using what I'm calling positive frequency solutions. So this will be clear in the next slides, in which I'll explain how to quantize those stuff. So with this separation of variables, you actually get a Schrödinger-like differential equation, and you can study it in the same way. So you can consider a wave, and you get this effective potential, which is a kind of barrier to the quantum waves that are propagating in your space-time. So how we are going to study that, how we quantize this thing. Yeah, we use canonical quantization, right? So you promote the field to an operator, and you expand it in this way. And this J is a collection of sets, so it's a collection of quantum numbers, which usually will be some collection of discrete or continuum of numbers. So in our case, it will be a angular quantum number, so L and M, but it can also be a continuous variable like omega, the frequency of the wave, of the mode. And those those operators A and A dagger will of course be particle and creation and annihilation operators. And you have to impose some commutation relations to get those commutation relations in the left left lower side of the slides. And so to do that, it's more or less involved, but it's not that hard. But I will skip those details. And of course, you can define a vacuum state by this lower equation, and the important thing here is that the vacuum state will be actually defined by the choice of functions you use as your mode functions, right? And so this will influence the choice of a vacuum. And in our case, we are actually using those modes as a basis, so what we call in modes. So I think a lot of you are actually familiar with that. So the in modes are the ones that are coming from past no infinity, and they propagate. Some part goes to the horizon, and some part goes to future no infinity. And so, of course, I use those from Schwarzschild spacetime. So actually what we are having here, we have modes that are coming from the past cosmological horizon. They propagate on the spacetime, go inside the black hole, and some part of the mode scatter back to the cosmological horizon. So those are the in modes. And what we call the up modes are actually similar. So you get something that is coming out of past horizon, so it's coming out from the white hole, and they scatter on space-time. Part of it goes back to the black hole, and part of it escapes the space-time via the cosmological horizon. And with that, you can study how you can compute the one particle emission amplitude from that. So we use perturbation theory, and you can compute it via this integral, right? Which basically, you are trying to compute the transition amplitude from going to the vacuum to the state of one particle, right? And in perturbation theory, this is the first term you get, non-trivial term you get. And so this J is something that you get from the orbiting source. And one interesting thing here is that if you compute this integral, you get something that's proportional to the Dirac delta of omega minus m capital omega. So capital omega is the angular velocity of the source. So what you are getting, that is only waves that are multiples of the capital omega can be emitted in this system. And the emitted power is calculated like that. So this capital T is the interaction time. So with that, you can try to compute some numbers. For instance, this here is the ratio of the emitted power calculated at the conformal coupling, which this chi equals 1/6, right? So I forgot to talk about that, but when chi is equal to 1/6 is the coupling value that you have conformal invariance. So this is what we call conformal coupling. And this is the ratio from the emitted power at conformal coupling and the emitted power at minimal coupling. And you can see here that as you increase the angular velocity, they are actually very similar to one another. So the angular velocity is the x-axis. But of course, when you decrease the angular velocity of the source, they start to get very unlike each other. And of course, this makes sense because as you decrease the angular velocity, you are actually distancing the source from the black hole, so you are getting closer to the cosmological horizon, right? And when you increase the cosmological constant, what's actually happening here is this ratio gets more, I would say, broad, right? So even for high angular velocities, you get something. The ratio is very is very different from 1 at some multipolar values. Another interesting thing here is, of course, you can vary the value of the coupling, right? And you can see that as you increase the value, you actually decrease the amount of radiation emitted. And another interesting thing is, if we look at this graph here with conformal coupling, as you vary the multipolar value, you get something that is actually the peak of the emitted power is actually increasing in this case here. So we can see that you are increasing the peak of the emitted power for this multipolar value, which is not something that happens in the minimal coupling case. So as you increase the multipolar value, actually you have a decrease of the peak for the emitted power. And I put this plot here just to show you that you actually get emit synchrotron-like radiation, right? Because as you truncate the emitted power at some value of L, you get more and more emitted radiation as your angular velocity is closer to the maximum, right? So, yeah, so I think this is the last slide, right? So this one is just to show you a little bit more that as you increase the cosmological constant value, you actually get less emitted radiation for the same value of the coupling. So some final remarks. Yeah, you get synchrotron radiation for all allowed values of the parameters. If you include non-minimal coupling, you reduce the amount of radiation emitted. And one interesting thing is that conformal coupling and non-zero cosmological constant is similar to minimal coupling and vanishing cosmological constant, which more or less makes sense, right? Because when you don't have a cosmological constant in minimal coupling, you are actually at conformal coupling in this case, because the equation is actually very similar. And so some perspectives is how to study orbits that are actually falling in the black hole, and what would be the effects on that, especially if you consider a very small space-time, that you get an orbit that comes basically from the cosmological horizon and orbits in spirals until it falls to the black hole. Yeah, so thank you for the attention and questions.
Thank you very much, Rafael, also for keeping the time.
Yeah, I think we looked at something, but I don't actually. Oh, sorry. So I can repeat the question. So Carlos asked if we look at a certain limit of the Schwarzschild de Sitter spacetime, it's the Nerei limit, in which you basically you try to collapse the event horizon and the cosmological horizon. And I think we looked at those limits, but I don't actually recall what was the discussion. Maybe João Paulo can say something about that, but
Or you can tell us about, if you want to just say a few words before we move on.
So when we take the limit to the extreme case, I think that's the case. So it keeps the same behavior as we saw for other values of the cosmological constant.
Nothing qualitatively different happens.
No.
Oh,